Good afternoon. We're back for another showing of algebraic connection, and we're still dealing with polynomials. We're going to review the rational root theorem. We're going to be introduced to the remainder theorem, and then we're going to get into graphing polynomials. And in graphing polynomials, we're going to find out the degree of the polynomials and the end behavior of these graphs. So let's review the rational root theorem. We talked last week about the rational root theorem being the ratio of the constant term, the factors of the constant term, to the factors of the leading coefficient. So the factors of 6 over the factors of 2, positive and negative. So these are our factors of 6, 1, 2, 3, and 6, plus or minus, and our factors of 2, 1 and 2, plus or minus. And when we simplify those, 1 over 1, 2 over 1, 3 over 1, 6 over 1, and you do the same thing over 2. And these are the possible values that you get as your possible roots. Remember, a root, if you're looking at a graph, is the x-intercept. So these are our possible roots: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, plus or minus 3/2. We go back to synthetic division to find these zeros. For the lack of time, we won't do all, but we'll check one. So the first one was positive 1. We bring 2 down, then we multiply. 2 times 1 is 2. Add these, 3 plus 2. 5 times 1 is 5. Add these. That's negative 6. Negative 6 times 1 is negative 6. That adds to give us negative 12. Whenever we have a root, our remainder should always be 0. So to keep in mind, to find a 0, if this is a 0, whatever number is here, if that is a 0, the remainder should be 0. To cut down on time, let's look at our possible zeros. 2 is a 0. If we plug in 2, bring this 2 down. 2 times 2 is 4. Add 7. 7 times 2 is 14. Add the negative plus the positive sign of the larger, that's subtraction, that's 3. 3 times 2 is 6, and if we add here, that is 0. So you get 0 for 2, so therefore 2 is a 0, or root, which also is the x-intercept on the graph. We do have other roots. Negative 3 can be a root. You will go through the same process. And negative 1/2. Let's show negative 1/2 since a lot of people get frightened over fractions for some reason. So negative 1/2. Bring down that first. 2 times negative 1/2. Half of 2 is 1. And it's negative, of course. Add. We'll get 2 again. Half of 2 is 1, and it's negative. That's negative 12. Half of 12 is 6. A negative times a negative is a positive. So this is 6, and therefore this remainder is 0. So these are my zeros for this polynomial function. The remainder theorem, the polynomial remainder theorem would do the same thing. The polynomial f of x can be divided by a linear term x minus whatever value we have for a. You will substitute, you evaluate for a in the function. So let's use the same function. And our possible values, we could take and plug those in. Notice everywhere there's an x, I place parentheses. We already know the roots are 2, negative 3, negative 1/2. Let's just try something different. Let's say negative 1. f of -1, we plug in for each x value -1. And -1 to the third power is -1 times -1 times -1. Negative times a negative is a positive, times a negative is a negative, so that is still 2 times -1. 3 times -1 to the second power is -1 times -1. So that's +1 minus 11 times -1 is -11 minus 6. 2 times -1 is -2. Plus 3 times 1 is 3. Minus -11 is just +11 minus 6. If we take all of these values, -2 plus 3, that's 1, plus 11 is 12, minus 6, that will equal 6. The remainder should be 0. In this case, it is 6. Well, we've proven that 2 is a remainder. So let's try 2 in. Plug 2 in each spot for x to evaluate. 2 to the third power is 8. 2 times 8 plus 3 times 2 to the second power is 4 minus 22, because 11 times 2 is 22, minus 6. So that is 16 plus 12 minus 22 minus 6. 16 plus 12 is 28. Minus 22 is 6. Minus 6 is 0. So notice we have 0 as our remainder, which means 2 is a 0, such as we found using synthetic division. So you can choose synthetic division or the polynomial remainder theorem to determine the zeros using the rational root theorem. To graph polynomials, we must know the degree of the polynomial. So the degree of a polynomial is the largest exponent of that variable. In this example, 4x to the third plus 2x squared minus 7, the degree is 3 because it is the largest exponent of this variable. If we had 4x squared y squared, this degree is 4 because it is the sum of the exponents. So that does come up from time to time. Now, here are the names of the different degrees and different polynomials we would possibly see graphed. A constant, just a number. The degree is 0. If the degree is 1, it is a linear term. If the degree is 2, it is a quadratic term. If the degree is 3, it is a cubic term. If the degree is 4, it is a quartic term. If the degree is 5, it is a quintic term. And most of the time, you hear up to cubic. After that, we say the number 4. The degree is 4, the degree is 5. So not to go too fast, let's look at it again. A constant has a degree of 0. A linear term has a degree of 1. A quadratic term has a degree of 2. A cubic term has a degree of 3. So graphs of polynomials, it's like kind of like driving a car. You have turns. You have turning points. The turning points can help you determine the degree of the polynomial. If a polynomial function has a degree of n, the maximum number of turning points is n minus 1. So if the degree is 5 5 minus 1 is 4, so it can only be 4 turning points. If the degree is 6, 6 minus 1 is 5, so that can only be 5 turning points. So if we look at these 3 examples listed, notice if this is a vehicle driving, just going straight, turn. Turn. So there are 2 turning points, which means the degree of this function is 3. The degree is one more than the turnings you see. Same situation here. Turn, turn, turn. That's 3 turns. 3 turns, therefore the degree must be 4. If you're driving down this line, there's a turn, 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 turn. 4 turns, so the degree must be 5. Another way I like to look at it other than the number of turns is actually counting the areas that each graph has. So there's an area here, that's 1. There's an area here, 2. There's an area here, which is 3. On this graph, here's the area, 1. Here's the area, 2. Here's the area, 3. Here's an area, 4. This graph, there's an area here, that's 1, 2, 3, 4, 5. So you can look at it from the number of turning points or the area to be able to recognize the degree of a polynomial. So, graphs of polynomial functions have n behaviors. There are certain things that you look at for graphs of polynomial function to help notice the degree and the possible other things of the graph. So, we've already talked about the degree. There's either even or odd degrees. 1, 3, 5, 7, 9, those are odd. Even, 2, 4, 6, 8, 10, those are even. If the leading coefficient is positive or negative, then they talk about the graph comparison. So let's look at the degrees. If there is an even degree, the graph will rise on both sides if it's positive. If it's negative, it will fall on both sides, meaning the graph will be even on either side. It will be the same on both sides. It will be even on both sides. If it has an odd degree and it is positive, it will fall on the left but rise to the right. Fall on the left and rise to the right. If it has a negative and it is odd, if it is a negative and it's odd, the leading coefficient being negative, it falls from left to right. It falls to the right and it rises to the left. So, what does that mean? That means as x approaches infinity, on a coordinate plane, we have our x number line and we have our y number line, x-axis, y-axis. Going this way for x is going towards infinity. So on and so on and so on and so on, you're going into infinity. If I'm going the opposite direction, that is going towards negative infinity. For y going up is going towards infinity, and going down is going towards negative infinity. So also with these, something else you can look at, the end behavior. If this was a graph, as it approaches, as the graph approaches x, is going towards positive infinity, and y is going towards positive infinity. As it's going negative infinity for x, y is going positive infinity. And these are some characteristics that give you. Same thing for even and negative. As x approaches positive infinity, y approaches negative infinity. And as x approach negative infinity, y approach negative infinity. Same thing with the odd positive. The characteristic for the end behavior is y, as x approach positive infinity, y approach positive infinity, and as x approach negative infinity, or meaning we're going in the negative direction for x, we would go in the negative direction for y. So if you get confused about the infinity and negative infinity, know that it's saying if you're going in a positive direction for x or the negative direction for x, if you're going in a positive direction for y or the negative direction for y. And the odd negative, as x approaches positive infinity, y approaches negative infinity. And as x approach negative infinity, y approach positive infinity. I understand this a lot, but those are characteristics you should know for the end behaviors of the graphs of polynomial functions. Let's look at some examples. Okay, just looking at the graph. First thing I like to notice, is it even or odd? Are my arrows going in the same direction? That means it's even or odd. Are these arrows pointing in the same direction? No, they're not. This is up, this is down. So that is an odd degree. This is up, this is down. This is also an odd degree. In this situation, my arrows are going in the same direction. So that is an even degree. And here also, even though it's going down, my arrows are going in the same direction. This is an even degree. What about my leading coefficients? Is it positive or negative? Let's look back at so if it's positive or negative, and we've said that this is odd, as x approach negative infinity, notice in the x direction going negative, y also goes negative. And as x goes to the positive direction, y goes positive also. So these are characteristics. So to go into our table to see which one it represents, this is odd but positive. Odd but positive. As x approach negative, y approach negative. As x approach positive, y approach positive. So therefore this is positive. Here, as x approach negative, y approaches positive, or it's heading in the positive direction, and as x is heading in the positive direction, y is going in the negative direction. This would make it a negative coefficient. if we have even degrees and the x is approaching negative infinity, negative, but y is going in a positive direction, so that is positive. X approaching positive infinity, y is approaching positive infinity also, or moving in a positive direction. This is positive. As x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y is moving in the negative direction. So this would be a negative, and we can relate all of this back to this information here on this table. I do understand this a lot. It's a lot at one time. So let's look at a couple of examples, and I'll give you a couple to do before we get out. All right, here's a graph. Which function belongs to this graph? Let's look at the same behavior we were looking at ahead of time. Is it an even or odd degree? Are they going in the same direction or different direction? It's the same, therefore it's even. The polynomial function is even. So we know it is even, it has an even degree, positive or negative leading coefficient. Well, it's even and it's facing down, so that is negative. As x approaches negative infinity, y approaches negative infinity. As x approaches infinity, y also approaches negative infinity. So now we have to determine the degree. We have to choose from one of these 6 functions to determine which degree will work. It is an even degree. This is the 3rd power. This is the 5th power. This is the 5th power. One, 2, and 5 are even degrees. So by process of elimination, that's all we have left. Okay, so the next thing is the leading coefficient is negative. The leading coefficient, what are the leading coefficients? 5, 6 is understood to be 1 right there, and negative 2. So by process of elimination alone, it has to be a negative leading coefficient. Both of these canceled out. So the polynomial for this has to be number 5. This is the polynomial function for this graph. So let's take a look at another graph before we head out. Graph B, positive or negative, even or odd, in behavior. We know it's not 5 because we've already chosen one for 5. Let's see if you can come up with the answer for graph B. Which one of these functions meet graph B? And the other thing would be graph C. Oh, graph C. Which one of these functions will be graph C? Once again, if you get the functions, you can hit me up on social media. I have Full Sackless gift cards with graph B and graph C. Tell me which function is which. Graph B and graph C. Twitter at CoachDJ2. Instagram at d.july2. Y'all have a good day, good week. I will see y'all next week.